In pursuit of sharing technical knowledge and just to gear up the new generation of engineers, myself, Pranav, is here to deliver today's presentation, Power Transformer Part 41. As the topic is of continuation, so for your convenience, the link of the previous one is given under the description box. Benefits of implementing OLTCs based on vacuum switching technology. Over time, vacuum switching technology has taken a new dimension both in the direction of the dimension both in the reactance type and resistor type OLTCs. Again, I repeat, over time, vacuum switching technology has taken a new dimension both in the reactance type and resistor type OLTC. The reactance type OLTC are in general external compartment type designs which are still predominantly used in the United States, operating on the low voltage side of the transformer at high currents. Because of external compartment type designs, so there is no special requirements with regard to physical size of the interrupter. But major implication in the process engineering on the part of the contact material selection and design, the vacuum interrupter has thus to be entertained an extensive optimization of the contact life, which is now reached to 6 lakhs operations. Vacuum's technique based newly developed in tank mounted resistor type OLTCs have shown their excellence in application and performance reliability. Resistor type OLTCs are mostly used in India and Asian countries as well as most of the European countries. The design principle so far been allowed is completely based on the diverter switch principle, where the diverter switch is handling the switching power under the hermetically sealed vacuum interrupter mechanism. However, the tap selector part is more or less identical to that of a tap changer conventional type. At the present concept, the performance level of newly designed vacuum interrupter has been drastically changed as due to have a major technological advancement in production process as well as proper selection of contact materials with changing its physical configuration in respect of the actual current to break. This has greatly reduced the size of the vacuum interrupters and also has to offer high reliability and long lifetime of the contact segments with a minimum maintenance and easy inspection. Due to have extremely low internal pressure in vacuum interrupters, only a small contact gap is thus to be maintained to achieve a high dielectric strength. The short arcing time has also to generate less energy, and because of a high rate of metal vapor recondensation process starts quickly, so altogether minimizes the contact wear process. As the resultant residuals caused by arcing are being contained within the hermetically sealed vacuum interrupters, so the insulating oil inside the diverter switch compartment would never be contaminated and kept always be clean. Overall intervals can then be extended up to 3 lakhs operations. Vacuum switching technology provides a superior dielectric advantages as because it has no interaction with surrounding medium. Under an extremely high number of switching applications at full load operation, vacuum interrupters have shown their superiority so far the safe operation is concerned. This is mainly achieved due to the extremely low loss of the contact material of vacuum interrupters. As high-speed resistor vacuum type OLTC for in-tank installations has been constantly entertained a maintenance free for up to 6 lakhs operations. So, in turn, that can deliver significant reduction of life cycle costs with increased transformer availability. Eminent manufacturers have claimed that specially developed vacuum interrupters may have to eliminate all sorts of oil degradation process, and at the same time there will be significant enhancement of contact lifetime up to 10 lakhs operations. In transmission network, there are the two most critical areas where invariably there is an emphasis on voltage regulation. Phase shifting transformers, which typically act to manage the control strategies of power flow in AC networks, and transformers for HVDC system as implemented for long distance transmission system and coupling of unsynchronized networks. At the present context, the importance of voltage regulation through OLTCs based on vacuum interrupter technology has become extremely demanding for the extensively applications of phase shifting transformers, HVDC system, electric arc furnace, etc. See the diagram, three-phase Dy11 tap changing transformer winding arrangement. Now, off-circuit tap changer, OCTC, or de-energized tap changers, DETC. Distribution transformer is particularly meant for the purpose of accomplishing the final voltage transformation in the electric power distribution system. This has done by stepping down the voltage to the level used by the customer. Basically, distribution transformer has configured with the short circuit impedance of the order of 4% to 6%. Whereas in case of power transformers, the short circuit impedance would have been of the order of more than 7%. The most important point is distribution transformer, as it is fed from power transformers. So, if the connected distribution transformer may have the higher short circuit impedance, then that will result in an unnecessary voltage drop across the power transformer. Now see the diagram, see the picture of off-circuit tap changers or de-energized tap changers. Such occurrence might have been restricted its ability to deliver power to its secondary connected equipment transformers. Such occurrence might have been restricted its ability to deliver power to its secondary connected equipment transformers. However, most of the distribution transformers have to install an offload tap changer, as because the required change in voltage generally would have become infrequent. Most important point. The offload tap changing is usually done manually, and the tap changing process may be facilitated by means of hand operated rotary or slider switch. As of figure 148, schematic of offload tap changer configured with studs marked 1 to 8 is categorically shown. It indicates that the transformer winding is tapped at 8 points. However, adjustment of tap setting is thus to be carried out only when the transformer is in de-energized condition. See the diagram of the no-load tap changer. First part A, you see A, the arm in the diagram, movable contact arm which operates by means of hand wheel mounted externally on the tank. F is the final position of the arm A to rotate. Note, to prevent inadvertent operation, an electromagnetic latching device or micro switch is thus to be provided to open the circuit breaker so as to de-energize the transformer as soon as the tap changer handle is moved, and that is to be actuated well before the contact of the arm with the stud opens. As of figure 148, 8 studs are suitably arranged on a faceplate which is thereby mounted on the transformer tank. Accordingly, winding of the transformer is tapped at 8 points, and each tap is a connection point along a transformer winding that allows a certain number of turns to be selected. So, the location of the faceplate is therefore to be positioned nearer to the taps of the windings. The winding, if it is tapped at the interval of 2% each, and as the movable contact arm A is moved over the studs, then the tap changer mechanism in transformers that allows for variable turn ratios to be selected in discrete steps. Blocking stud suffixed as F would have the position where from arm A cannot be moved to rotate further in clockwise direction, and thus no possibility is there to bridge studs 1 and 8 by the arm A. Arm A moved over to studs 1 to 2. Then the winding in circuit, then 100% of winding is in circuit. 2 to 3. 98% of winding is in circuit. 3 to 4, 96% of winding is in circuit. 4 to 5, 94% of winding is in circuit. 5 to 6, 92% of the winding is in circuit. 6 to 7, 90% of winding is in circuit. 7 to 8, 88% of winding is in circuit. Salient points. On-load tap changer has the ability to perform voltage regulation system very fast, and that can be adjustable at any time. For a complete one tap position shift, it takes only 4 to 5 seconds and can have to switch the load within 40 to 50 milliseconds. On-load tap changing mechanism has to follow the make before break switching arrangement, as because it must be ensured that the transformer winding would never be in open circuited condition during the process of tap changing operation. Off-load tap changer is usually configured with simple switching mechanism mounted close to the winding tappings, and the main tapping assembly are being kept under oil. It has been so designed that the change of tap position can only be done when transformer must have to be in de-energized condition. This is the basic difference in between on-load and off-load type tap changers. Hence, off-load tap changing is not at all follow the process of make before break type switching. If the load tap changing process would have been somehow made to carry out while the transformer is at energized condition, then there must have a heavy spark over in between the winding taps, causing a severe damage of the winding itself as well as transformer insulation part. In high voltage distribution system, off-load tap changer is also to be installed at the transformer high voltage side winding, and that has to be accommodate transmission system variations within a narrow band around the nominal rating. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.